Hello everyone, I'm Ruoyu. Today I'm gonna present DnD, a cross-architecture deep neural network decompiler. Deep neural networks, DNNs, have been implemented and deployed on many devices to support many applications, such as facial recognition, speech recognition, and anomaly detection. When deployment, dedicated compilers are used to compile the DNN model into binary, such as GLOW and TVM. These binaries are usually deployed on edge devices, such as a face recognition camera. In this work, we explore the possibility of decompiling DNN binaries. DNN binaries decompilation has many security applications, such as stealing DNN models and turning black box adversarial attack into a more effective white box adversarial attack. For example, the figure below shows that after adding some imperceptible noises, the DNN model will misclassify a stop sign as a teddy bear. Before we discuss about DNN binary decompilation, let me first give some backgrounds. The figure below shows a snippet of a ResNet model in ONNX format. The ONNX format represents a neural network as a computation graph. Each node in the graph is a DNN operator. The DNN operators are the building blocks of DNN. There are various types of DNN operators with different mathematical semantics. Currently, there are 174 different operators defined in ONNX. It includes convolution, average pool, and ReLU. DNN model semantics include operator-level semantics such as type, attributes, and parameters. And model-level semantics include topology, which defines how the operators are connected with each other. To compile a DNN into binary, ahead-of-time compilation is usually used. It specializes the operator according to its attributes and parameters. For instance, here the highlighted convolution 2 and convolution 3, although they share the same operator type, but because of their different attributes and parameters, they are compiled into two different binary functions with very different control flow and data flow structure. General purpose decompilers are used to recover C-language level syntactics from the binary. However, they have several limitations when dealing with DNN binaries. Here we show a snippet. Here we show a code of IDA-Pro decompilation results of a single convolution operator instance. As you can see, it contains 348 lines of code with multiple long loop bodies and many bitwise operations. If I were a reverse engineer, I have totally no idea what this function is doing. Instead, our system DnD can recover high-level DNN semantics from the binary and output the DNN model in ONNX format, such as the figure below. It includes all the high-level semantics, such as operator type, attributes, and parameters. DnD's objective is to recover DNN models in ONNX format from the binaries running on CPU devices. It should be generic to support different compilers and ISAs, and it should be accurate to recover DNN models with high accuracy. Let me first give an overview of our pipeline. At the very beginning, given a DNN binary, we locate the binary function that implements the DNN operator. And for each allocated operator function, we generate an operator summary represented with the IR we design, which is capable of capturing its mathematical semantics. And at the very last, we recover the high-level model semantics and output the model in ONNX format. And now I will give some details of each step. In the first step, we look for the binary function with certain structures, including nested loops and vectorized computations. These functions are identified as the function that implement the DNN operator. Note that our system works at the binary level but for easier understanding, we will show in source code as our running example in the following slides. And in the next step, we generate an operator summary for each located binary function, which captures method semantics. To do so, we first conduct a loop analysis to identify the induction variables and their information. Induction variables are also called loop index. For example, they are the variables I, J, U, V shown in the figure. And we also identify their information such as initial value, step size, and loop count. Then we symbolize the identified induction variables and conduct symbolic execution to extract an expression that represents the output of this function using its input and parameters. For example, here it is the expression we extract from this binary function. Then we leave the extracted expressions into operator summary represented with our IR. For example, here we leave the expression on the left to the operator summary on the right, where we replace the plus equal on the left to the summation function defined in our IR, and multiplication with multiplication function in our IR. We also attach the induction variables, indicating all the possible ranges of each loop index. For instance, for the variable u, its ranges is from 0 to 1. And after operator summary generation, we finally recover the DNN high-level semantics. First, we recover the operator type for each operator function with AST matching. We have a reference AST database in advance, which maps each operator to its corresponding AST. For instance, here's the reference AST of a convolution operator. Then we match the AST in operator summary with all of the reference ASTs. We consider the operator type as that of a reference AST if their ASTs are matched. For instance, here we match the AST included in the operator summary with the reference AST of convolution, and it succeeds. So we consider it as a convolution operator. We then recover the DNN topology by leveraging the data dependencies between each DNN operator function. For instance, here we identify that the output of convolution 1 and the input of convolution 3 are pointing to the same memory address. So we infer there's an age from convolution 1 to convolution 3. At the very last, we recover the attributes and parameters of each operator function by leveraging the operator summary and the recovered DNN topology. For instance, here we recover the values of filter by extracting from their corresponding memory address. In evaluation, first, we evaluate generality by evaluating how many widely used DNN models we can support. We consider model supported when all of its operators are supported. We collect 37 DNN models from ONNX and MLPerf tiny benchmarks, covering 70 DNN models. Covering 70 DNN operators. And our evaluations shows that our system can support 84% of operator. It in turn enables support for 81% of the models. We also evaluate the correctness of a system by checking if our system can decompile a DNN model and generate a model that is equivalent to the original one. We test with 15 DNN binaries. They are compiled with 2 compilers, 3 ISAs, and 3 models. We compare their inference results given 10,000 test inputs. And our evaluation shows that we can decompile all the binaries with 100% accuracy. For example, here we show the architecture of the original ResNet model and the architecture of the decompiled ResNet model generated by our system. And as you can see, they have the identical architecture. And we further test with 10,000 input and show that they have the same inference behavior. We conduct case studies on a real-world microcontroller where a ResNet model is deployed. we show that our system can successfully steal the model from the board. Specifically, we dump the binary from the board and decompile the binary with our system. And we verify the correctness of the decompile model by showing that they have the identical inference results. We also show that the decompile model can be used to boost adversarial attack. With the decompile model, we launched white box attack, which successfully reduced the accuracy from 88% with the original input to the 11% with the white box input, while the black box attack can only degrade accuracy to 57. In summary, decompiling DNN binaries requires customized techniques with DNN-specific knowledge. We propose DnD, the first decompiler for compiled DNN binaries, and it is open source on GitHub. And thank you. I'm ready to take questions.